Okay, so here we are back at this picture. I've sort of jazzed it up a little bit here. What I want you to see in this picture is every single one of these cross sections is perpendicular to the x-axis. So if I change my color here for a second, right in here, here's my x-axis along the bottom, here's my y-axis along the top. This is really fuzzy, but I think they're looking at the graph of y equals x squared, which you've certainly studied a lot in your math life. So every single one of these images here, these four like really great pictures, all of these cross sections are taken perpendicular to the x-axis. That's important. You have to be told whether it's perpendicular to the x-axis or it's perpendicular to the y-axis. So we're going to build the volume formula very generically so that you can handle any cross-section shape. So what I want you to know with these cross-sections is that if I think about the cross-section itself, and I'm going to kind of pay attention to this guy right here, that's a square. So I'm going to think about the volume of that sort of 3D cross-section. It's sort of, the cross-section is a square. Cross-section is a square. I'm going to kind of move over here, give myself some more room. And so when we think about that, the actual volume of that cross-section is kind of like a rectangular prism. So what I want you to think of for the volume, and this is very generic, but this works for anything. I want you to think about the volume of that rectangular prism or square prism is it's the area of the cross section itself, meaning it's the area of a square, and then you have some kind of like depth or height, however you want to view what that is. I guess I'll put a little height in there. Depends on just that extra dimension. So when I mean height, I mean, how thick is it? So that's how I want you to think about all of these guys. We're going to talk about the volume formula in general, building the volume formula from cross sections. And I want you to think about volume as the area of the cross section times the height. What I want you to notice in this first example here is that height I'm referring to is right here. And think about that pink rectangle that I've drawn in the shaded region, mind you. It's some little like change in x on the x-axis. That's really important. So that height, it either morphs into a delta x, and that's if it's perpendicular to the x-axis. Notice that rectangle in there is a vertical rectangle. So you know what I'm going to put over here? I am going to put a vertical rectangle. If you have a vertical rectangle, you know that eventually your integral is going to be in terms of dx. Now, if I was perpendicular to the y-axis, so maybe I'll show that on this last picture over here. Maybe I'll use this lavender color. So perpendicular to the x-axis would be a totally different shape. I can still think of it as squares if I want to, but you're going to be in the shaded region here. And so perpendicular to the y-axis would make my square kind of look like this. And so if I think about it, that idea of the height is up in here. Okay, that's my height. That's some kind of change in y value. So the height either takes on, it either becomes a delta x or a delta y. And so that would be if I was perpendicular to the y-axis. Notice that rectangle that I drew in purple happens to be a horizontal shape. So everything that we just talked about with disk and washer, if you set up your rectangle in the shaded region and it's drawn vertically, your integral is going to be in terms of the x variable, and you're going to get your limits of integration from the x-axis. If you draw your rectangle in the shaded region and it's horizontal, that means your integral is going to be in terms of y, and you're going to get your limits of integration from the y-axis. So that's wildly consistent through this entire process. So if I want to find the volume of these cross sections as I have them, I want you to think about the volume of any of these shapes. It is going to be an integral. We're eventually going to say, hey, I want these rectangular prisms to be as thin as possible. I want that delta x to become a dx, and I want that delta y to become a dy. This is where it kind of runs into that integral. And we're going to set up the formula as basically it's the area of the cross section that was described to you in the problem. And it's either going to be dx if your rectangle was drawn vertically, or dy if your rectangle happened to be drawn horizontally. So you want to kind of pay attention to that area of the cross section, because every problem is different. I can't, tell you exactly, what you're going to see. I can definitely tell you the common shapes that there are, but you want to review some of these cross sections down below here. Really pay attention to those cross sections that you've got. I'm going to kind of keep referring to them, the areas of these cross sections with the idea of a side, meaning like how long is that rectangle in there? I'm going to call that a side. And I'm going to run through some of those formulas over here. So if you're talking about a square, I know you guys know what the area of a square is. The area is just the side length squared. So I'm going to write it like that, side squared. Now, if you have a semicircle, this is the one that's kind of weird. You have the semicircle in your region. I know you know the area of a circle is pi r squared, but notice that r is half that rectangle length. So what I'm going to do is say, look, I'm going to call the whole thing here the side. So my area of a semicircle would be, well, half the area of the circle. And I'm going to write pi, instead of r squared, I'm going to write side divided by 2 squared. So that's kind of a mouthful in there. Also noting that this is the only guy that has a pi in it, and it's because of the cross section being a semicircle. Remember, none of these volumes were spinning anywhere. This is our only cross section that has a coefficient of pi. That's important. Okay, if I go over here to this isosceles right triangle, you can kind of see they're marked here that those are the same. That's nothing more than your area of a triangle, which is 1/2 base times height. If it's isosceles, and again, I'm calling this the side, then I'm going to think about that area as 1/2 side squared. Okay, and over here we're going to have some cross sections that are going to be described to you in a way. This one, they're going to say the rectangle has a length in our region, and the height is 1/2 that length. Again, I'm going to kind of refer to this as being a side, and I'm going to think about that area is length times width, so that would be 1/2 side times side, so that's 1/2 side squared. You kind of have to get your geometry on in here and sort of think about the cross section that you're given and create that area of the cross section. Very, very generic shapes that they tend to use. They do like to use the squares. They do like to use those isosceles right triangles, the rectangles. I've seen a good amount. We'll talk about some of those semicircles in there. These are your classic shapes. All right, so we'll get in there and do some of the examples that you see in this pretty nice picture that somebody